In the previous video, we started our discussion of how the design process of a hybrid PV tandem device takes place on experimental level. We considered the band gap tuning of the amorphous silicon top cell and the challenges for material processing. The optical aspects of such hybrid device need to be considered as well. We have added the typical values of the refractive index for these materials. The organic material, the molybdenum oxide and the zinc oxide layers have a significant lower refractive index in the reference to the back reflector and the silicon top cell. This means that an optical cavity is created in this relatively flat thin film device. It will optically operate in the diffractive regime. The absorption of the bottom cell depends on the interference effects and is determined by the thickness of the optical cavity, the refractive index of the optical cavity, the refractive index mismatch with surrounding media, and the wavelength. What thickness should be chosen for top and bottom cell? Optical simulations need to be performed to optimize the thickness for the top and bottom cell. The solid line and the dashed line correspond to the current density of the bottom cell and the top cell as a function of the thickness of the bottom cell. The bottom cell has a maximum in its current density around the thickness of 150 nanometers in this graph. The current density in the top cell is less sensitive to the thickness of the bottom cell. These results correspond to a top cell thickness of 100 nanometers. Nevertheless, the top cell is current limiting if it has a thickness of 100 nanometers. The thickness of the top cell is now increased to 200 nanometers. The current density of the top cell increases while the wavelength dependence of the current density of the bottom cell remains the same. The top cell is still current limiting. Therefore, the thickness of the top cell is increased further to 300 nanometers. The current density of the top cell increases further without affecting the dependence of the current density of the bottom cell. If the thickness of the top cell is increased to 400 nanometers, we can see that a bottom cell of around 150 nanometers would result in a current matched tandem cell. These optimal thicknesses have been used to create a tandem cell of a 400 nanometer top cell and a 150 nanometers bottom cell. Here we see the IV curve of the amorphous silicon single junction solar cell, the organic single junction solar cell, and the hybrid tandem solar cell. The tandem solar cell results in an 11.6 efficient solar cell. Here you see the scanning electron microscope picture of a flat triple junction. The device configuration is based on a tandem cell including an additional amorphous silicon middle cell with a lower band gap in reference to the top cell. First ITO, then the amorphous silicon top cell, followed by amorphous silicon middle cell and the zinc oxide electron collecting layer, the silver recombination layer and the molybdenum oxide hole collecting layer, the organic bottom cell and the back contact are shown. To facilitate the light trapping in the middle cell while preserving the electrical properties of the organic bottom cell, a moderately textured device structure needs to be developed. The entire device structure has therefore been deposited on a moderately textured zinc oxide substrate, as you can see here. This SAM picture shows the moderately textured hybrid amorphous silicon OPV triple junction. You can see clearly the moderate texture at the interface in reference to the flat device. In this graph, the typical JV curves of the amorphous silicon tandem cell as a reference and the amorphous silicon OPV triple junction is shown. A typical EQE of such device is depicted as well. The current densities are reasonably distributed over the three junctions, so are close to current matched. The maximum conversion efficiency obtained is 13.2%. This device demonstrates that the higher bandgap energy utilization of an amorphous silicon solar cell indeed results in higher conversion efficiencies for the triple junction solar cells. In this example, 13.2% has been achieved. This demonstrates that if the similar bandgap energy utilization for the high bandgap organic materials can be realized, higher conversion efficiencies can be expected for organic solar cells. And this is indeed the case, as last week I've discussed that the German company Heliatech had demonstrated recently a conversion efficiency of 13.2% for an OPV-based triple junction. The details of this device have not been released. However, considering the results presented here, it is likely that the improvement in the high bandgap material was responsible for the increase in this efficiency.